The flamboyant cuttlefish is a beautiful animal. Although this ocean-dwelling invertebrate evolved on a different evolutionary path millions of years ago, it's actually similar to humans in some ways. Hi, I'm Dr. Maria Conley, and today I'm going to talk about how an increasingly complex blood pumping system evolved in animals from cuttlefish to humans. We'll see how land animals developed higher blood pressure to deal with gravity and why a giraffe in particular has such a high blood pressure. The cephalopod mollusks, including cuttlefish, octopus, and squid, circulate blood in a closed system much like humans do. In a closed circulatory system, blood is contained inside blood vessels rather than flowing freely in the body as you would see in an open circulation of most animals without a spine or other invertebrate animals. With closed circulation, an animal can pump blood at higher pressures. The cuttlefish also has developed a dual pressure blood circulation. Like humans, it has a higher systemic blood pressure to efficiently pump oxygen to the rest of its body while it moves blood at a lower pressure through its gills. This allows oxygen to pass into the blood effectively. Instead of using a single four-chambered heart to accomplish this, as we do, cuttlefish use three dual-chambered hearts, including one systemic heart and two gill hearts. The systemic heart pumps oxygenated blood arriving from the gills to the rest of the body. The two additional gill hearts each pump deoxygenated blood back to their respective gill. However, the blood pressure in a cuttlefish averages only 44/22 millimeters of mercury. In humans, normal blood pressure is approximately 120/80 millimeters of mercury. Why is there such a big difference in blood pressure among water-dwelling invertebrate animals versus land-dwelling vertebrate animals or animals with a spine? In general, higher blood pressure is required to overcome the force of gravity, maintain a constant internal body temperature, and a high metabolic rate as seen in many land animals. As vertebrate animals evolved from living in the sea to walking on land, their blood pressure increased. At the same time, the blood pump or heart evolved from a two-chambered heart in fish to a three-chambered heart in reptiles, and finally to a four-chambered heart in mammals and birds. The blood pressure of an animal living in water does not have to be that high in order to effectively pump nutrients and oxygen throughout its body. In water, an animal is virtually weightless. Since the density of water and blood are similar, the pressure that the blood exerts inside blood vessels is counterbalanced by the pressure of the surrounding water. However, in land animals, the downward force of gravity causes the pressure in a vertical column of blood in the body to be highest at the lowest point, like in your feet. Vertebrates developed increased blood pressure to counteract gravitational force. All the organs of your body, particularly your brain, need a constant supply of oxygen. If your brain is significantly higher than your heart, like in a giraffe, for example, or us, you'll need to have a higher baseline blood pressure at the level of your heart to get an adequate amount of blood up to the brain. So just think of the giraffe again, who must generate an arterial blood pressure of 200 millimeters of mercury at the level of the heart just to pump an adequate amount of blood up to the brain, which is typically at least 2 meters higher than its heart. Once the blood gets to the giraffe's brain, the systolic blood pressure has dropped to approximately 100 millimeters of mercury, which is really close to the minimal amount of blood pressure needed to avoid loss of consciousness. The situation is similar in humans and other mammals, although less exaggerated or extreme. It is a closed circulation of vertebrates that is able to generate these higher pressures. In contrast, in most animals without a spine, with the exception of the cephalopod mollusks like the cuttlefish, most of these animals have an open circulatory system which generates pressure less efficiently. A closed circulation also enabled birds and mammals to develop bodies which could be maintained at approximately 37 degrees Celsius. Obviously, maintaining a high body temperature requires a higher basal metabolic rate, which also requires a higher blood pressure. As a group, birds tend to have the highest metabolic rates and thus the highest blood pressures. So we could see that blood pressure increased as the circulatory system evolved from the open system of many aquatic invertebrates, such as crabs, clams, and sea slugs, to a closed circulatory system as seen in animals living on land, such as humans and birds. When animals gained a spine and migrated to land, their average blood pressure also increased to counteract the force of gravity pushing down on them. So why did cuttlefish, which are so far removed from the human species in the evolutionary tree, develop such a sophisticated circulatory system? This may be an example of convergent evolution where two very different types of animals, humans and cuttlefish here, independently develop the same body adaptation, closed circulatory system, to cope with their environment. Thank you for listening. I hope that this is helpful for you.